Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate. We are all familiar with the concept of boiling. You see a pot of hot water boiling on a stove. However, to get to boiling, it's a long process for water. And it requires several intermediate steps, which I will all describe in today's video and then culminate with the process of boiling itself. This is a very important topic because everybody should know what boiling is. Now, we have to start by describing what boiling is not, basically. So if we have here a glass of water, and let's say temperature is 10 degrees Celsius. Water will not boil, of course, at 10 degrees Celsius and standard pressure around us, let's say pressure of 1 atmosphere, 1000 hectopascal. But what will happen is that if this is liquid water and this is air, that randomly there will be some molecule of liquid water escaping into the air, becoming water vapor, and randomly some water vapor molecule, if it has the right direction of motion, will enter the liquid water. And this is what I discussed in previous videos. This is evaporation, this is condensation. If the rate of evaporation equals the rate of condensation, we have thermal equilibrium, and the amount of water in this glass will stay unchanged. If the rate of evaporation exceeds the rate of condensation, we will have net evaporation and the water will evaporate from the glass. This is not boiling. So this is very, very important to understand that. Now, from this, we can extend a little bit this concept to other gases in the atmosphere. And this is already a little bit connected, as we will see later, to boiling, but not yet boiling. What do I mean by that? So here is this liquid water interface between air and water. Let me erase this here to have more space. So air, water. Now, we know from my previous videos that what is air? Air is nitrogen, 78%. Oxygen, 21%. And other gases, there is CO2, there is argon, there is water vapor, and so on. So this air over here will have 78% of nitrogen. So let's say nitrogen I indicated with these squares. Just like this water vapor randomly entered liquid water, well, this nitrogen can also enter liquid water. If this nitrogen enters liquid water, we say that this nitrogen is dissolved in water. Similarly, this oxygen, let's indicate it with asterisk, can enter water if this molecule has enough energy and it is moving towards the water, it can enter water. So we would say that here we have dissolved nitrogen and dissolved oxygen in water. Well, similarly, if there is some oxygen over here in water, it can escape water randomly. So we would say we have equilibrium between dissolved oxygen or nitrogen, dissolved gas in water, and concentration of that gas above water. So the question is, listen to this carefully, the question is, how much dissolved gas you can have in liquid water? The answer is Henry's law. So this is new law we are introducing. Henry's law tells us how much dissolved gases you can have in liquid water. Very important law, particularly if you are doing scuba diving. When you take scuba diving lessons, they will talk about Henry's law a lot. Because if you do not obey Henry's law, you might die in scuba diving. So very important law. And you will learn more about it here. Without deriving law, because this is fundamental playlist, I can tell you that the Henry law says that C, concentration of dissolved gas, nitrogen, oxygen, argon, CO2, in water, whatever, is equal a certain constant, Kh, which is called Henry's constant, times pressure of the gas above liquid water. Very, very simple law. I will raise this to have more space. Now, so I said the amount of dissolved gases depends on Henry's law, but let's now explain that more physically. How much dissolved gases Henry's law tells us we can have? Well, that depends on the pressure of the gas above the liquid water, P. So the more gas we have above liquid water, the more can be dissolved. That makes sense. That makes sense because if we don't have any gas above liquid water, if there was no nitrogen, then how could nitrogen be dissolved? So the more nitrogen, the more potential to be dissolved. But it also depends on this constant Kh. And this constant Kh depends on temperature. So it's really not the actual constant. It's a constant for a given gas and given temperature. Changing gases and changing temperatures changes this Kh. Different gases have different solubility in water. For example, CO2 dissolves much easier than nitrogen. But I would like to discuss here what is very important, dependency on temperature. As temperature increases, then this constant Kh will decrease. And this is very important. This is crucial. How is that crucial? In the following way. I will replicate this figure here. Think about it, what I just said. I have dissolved gases in water. Now, I increase temperature of water. That means Kh will decrease. That means concentration of these dissolved gases will decrease. Well, that means some of these gases, let's say nitrogen, will form a bubble and it will escape. And this is called degassing. Because I didn't do anything to the air, air still has 78% nitrogen, whatnot. But I did something to water, I increased temperature of water. Well, if I increase temperature of water, Kh dropped, which means C dropped. This P is constant, it's 78% associated with pressure of nitrogen. So these nitrogen molecules that are in water will group in a bubble and escape. And similar process will occur, for example, for oxygen bubbles. Here are nitrogen bubbles. And this process is known as process of degassing. In other words, Henry's law tells us that when we increase temperature, we broke the thermal equilibrium between dissolved gases in liquid water and their vapor state in the atmosphere. And because we broke the equilibrium, this liquid can contain less of these gases, so the excess will escape through small degassing bubbles. Can you see degassing bubbles? Yes, you can see degassing bubbles. When you heat water, before boiling, when water is hot but not boiling, you can see small bubbles initiating at the bottom of the pan and moving up. Why are they at the bottom of the pot? Two reasons. Reason number one, these small bubbles typically form at irregularities, scratches, impurities close to the container that holds water. That's the best place for them to form. But reason number two, if I am heating this water, I'm heating it from underneath, typically on a stove. That means water is the warmest here. Well, water is the warmest here means that the solubility of water for these gases is the smallest here. So it's much more likely for this bubble to form close to the bottom than at the top. In fact, if you have very deep pot in which you are warming water, this is very interesting, then those degassing bubbles can form close to the bottom of the pot, and by the time that they reach the top, they can disappear because water at the top is cold enough for these bubbles to be destroyed. In other words, the gas will dissolve again in water because of the temperature gradient. Now, it is also from the dynamics physical point of view, it is very important to understand that the pressure in these bubbles needs to be such, let me erase, needs to be such to overcome external pressure of the atmosphere plus the external pressure of liquid water. What do I mean? Very simple. If this is that container, here is the liquid water surface, and here we have a small degassing bubble that formed. Well, here we have atmospheric pressure P, let's call it P atmosphere. Here we also have P of, we call that hydrostatic pressure of water, P water. And there is also a surface tension pressure of water trying to crush the bubble, which I discussed in one of the previous videos, surface tension. Now, there is pressure inside of this bubble. So this internal pressure, let's call it internal pressure in the bubble, and this bubble might be formed by nitrogen, degassing. This internal pressure in the bubble needs to be at least equal to surface tension pressure, ST, plus hydrostatic pressure of water plus pressure of the atmosphere. If that is not the case, then this bubble will be crushed, it will be collapsed. And the buildup of surface pressure, the buildup of internal pressure in the bubble is governed by the temperature, which governs the amount of dissolved gases in the liquid. Okay? So this is called degassing. How is this related to boiling? Well, boiling, let me erase this. Boiling happens in the following way. If we have this container of liquid water, and here is air, here is liquid water, and we increase temperature of the water to a critical point, which is typically around 100 degrees Celsius when the pressure is about 1 atmosphere, then we will have spontaneous formation of bubbles, but these are pure, not almost pure, water vapor bubbles. Now, these water vapor bubbles have partial pressure of water vapor, E. You remember we said E is partial pressure of water vapor. So let's say these are water vapor molecules inside of that bubble. This water vapor pressure inside of the bubble is equal saturation vapor pressure that depends on temperature, what we discussed in great details in my previous video. And now the key concept. This saturation vapor pressure, this vapor pressure inside of the bubble needs to be equal, approximately equal to the atmospheric pressure. More precisely, atmospheric pressure plus hydrostatic pressure of water plus surface tension, what I discussed here before. In other words, when the vapor pressure inside of the bubbles, which is always saturation vapor pressure, because this is more or less pure water vapor, is equal to atmospheric pressure, we have boiling. And this bubble of water vapor can escape into the air. How is this related to degassing? Well, it is related to degassing because this bubble of boiling water vapor, boiling water, is usually associated with degassing bubbles. These small degassing bubbles serve as embryons for water vapor bubbles in the process of boiling. Okay? Why is that the case? Well, that's the case because these degassing bubbles already have gas-liquid interface, which is difficult to form. So the water vapor bubble, instead of forming new liquid-water interface, it can just use the liquid-water interface that was formed by degassing bubbles. And that's why I said it's almost pure water vapor. Not quite pure, because in this boiling water vapor bubble, there are also dissolved the gases that are no longer dissolved, like nitrogen, oxygen, and so on. Okay? So that's how the process of boiling happens. Namely, the partial pressure, which is equal saturation pressure at a given temperature, needs to be atmospheric pressure plus hydrostatic pressure of water plus the surface tension pressure of water inside of the liquid. Okay? So now you can also see why water boils at lower temperatures at altitude. Because if you go on top of a mountain, then the pressure is not 1 atmosphere. The pressure is maybe 0.9 atmospheres. Well, that means that this saturation vapor pressure inside of the bubble doesn't need to reach 1 atmosphere, 1000 millibars. It can reach 900 millibars and we will boil. Now, if the atmospheric pressure is very high, if it is theoretically, 1.1 atmosphere, that's very, very high. But if it would be 1.1 atmosphere, then you would have to exceed 100 degrees Celsius for water to boil, because you need to provide enough energy for these water molecules to form vapor inside of the liquid to exert pressure larger than 1.1 atmosphere or 1100 hectopascals. Okay? Now, what else to say about the process of boiling? Well, we can even better connect boiling with degassing. And that's through the concept of the superheated water. In one of the previous videos, I discussed supercooled water. That's water being liquid below 0 degrees Celsius. Well, water can stay also liquid, namely, water can be without boiling above 100 degrees Celsius and 1 atmosphere. How is that possible? Well, that's possible if the water is pure. If the water is distilled pure water. That means there is no gases in the water that are dissolved. And that means that there are no these small bubble embryons of degassing that would attract boiling bubbles to form around them. And that means if you put, for example, distilled water in microwave, which you should never do. If you put distilled water in microwave, you can heat it above 100 degrees. But what will happen is something extremely dangerous. That water can explode. Because water is, let's say, 120 degrees Celsius. It wants to boil, but it doesn't have degassing embryons to form boiling bubbles. And at some point there will be some random fluctuation, some random impurity in water that will initiate boiling, but because temperature is so high, that boiling will be so vigorous that you will have explosion. So you should never do it. That's called the concept of superheated water. Water above 100 degrees Celsius but not boiling, because it's pure. There is no impurities to initiate boiling. Similar concept we discussed for supercooled water below 0 degrees Celsius. Check that video, please. Lastly, what is the saturation vapor pressure of water vapor at boiling? Well, it's 1 atmosphere. Around 1000 hectopascals. Okay? You remember that saturation vapor pressure at 0 degrees Celsius is 6.1 hectopascals. I discussed that in one of the previous videos. So you see, This is also, if you have water at 0 degrees or 10 degrees Celsius, then saturation vapor pressure is, let's say, 10 hectopascals. What does that mean? That means if somehow, if you have water at 10 degrees Celsius, and somehow there is bubble of water vapor that formed inside of the liquid, well, the pressure in that bubble is 10 hectopascals. That is much less than 1 atmosphere, than 1000 hectopascals. So that bubble gets crushed immediately. In other words, in a glass of water that sits in front of you, and water temperature, I don't know, tap water, 20 degrees Celsius. If randomly some bubble of water vapor forms, pressure inside of that bubble is very low, much lower than 1000 hectopascals, and atmospheric pressure immediately collapses it. However, when we increase temperature, then this saturation vapor pressure increases exponentially through Clausius-Clapeyron equation that I discussed in one of the previous videos, and at some point this saturation vapor pressure will reach 1 atmosphere. And then this bubble says, atmosphere, you cannot destroy me anymore, because my internal pressure is equal to your pressure, and I will survive. Of course, there is also this hydrostatic pressure of water and surface tension that I'm neglecting, but conceptually you understand what I'm talking about. So this explains naturally the concept of evaporation, degassing, superheated water, and then consequently the process of boiling. Please make sure to like and subscribe. Stay tuned until the next video. Share, comment, and until next lecture, goodbye.